In this video, I'm going to explain my faster-than-light framework for space travel that I've been working on. The computational development of this framework in my spare time led me to invent the pulse generator. I want to explain the idea to you. There are generally two major theories about going faster than light to get from any 2 points A and B in space. The first is to generate a huge amount of energy, similar to how a gun works, to blast through the light barrier at warp speed. This is a hard theory to continue since, according to scientists today, and as I'll explain in this episode, getting to light speed would immediately consume an infinite amount of energy. The second approach is to basically travel back in time from point A to an older gravity, when the universe was much smaller, travel the much shorter distance between A and B quickly using standard engine power, and come back through time to point B. The major problem with this theory is, well, everything really, including the requirement for time travel. So I decided to investigate the first theory of generating a huge amount of energy to pass through the speed of light barrier. In the last episode, we talked about Albert Einstein and his beautiful theory of general relativity and his famous equation E equals mc squared. Einstein often used what he termed thought experiments to try to answer the question he had about the universe around us. Einstein said his thought experiments as a teenager drove the development of his theories of relativity. Einstein's most famous thought experiment was that he imagined he was chasing a beam of light through space. As he traveled faster towards light speed, the mass around him appeared to be getting relatively larger, while in contrast, the time he moved in slowed down. When Einstein caught up with light speed, time was still and so essentially ceased to be, while the observed mass around him became infinite. This means the speed of light is generally considered the fastest energy known in the observable universe. So why do I dare think FTL energy exists? I imagined I was riding with Einstein chasing the light beam and started to wonder how it was possible for Einstein's observations not to integrate with light when he reached the speed of light. Seemingly nothing else could exist but light at light speed, since it's the terminal speed of all energy in the universe. However, when Einstein reaches the speed of light, he is still able to observe the phenomenon occurring around him. So how does his observation still work at light speed? Another way of framing the question is to try to understand how, in the famous equation E equals mc squared, if the constant c is the speed of light and is both the fastest energy in the universe and uses an infinite amount of energy when its top speed is reached, then how is it possible, or at least practical from a computational point of view, to square it for any energy particle at rest? It would seem we have no capacity to get any faster or any more energy if we're already at terminal speed and are using an infinite amount of energy already. But what if the observation Einstein was making while chasing the beam of light was happening at speeds faster? What if our observation or our senses in general were partly functional and based on an FTL energy and correlated mechanism within gravity and light, but operating in another dimension, one that we're not aware of yet? If such an energy existed, it would explain how Einstein was still able to observe the phenomenon while traveling at the speed of light. But assuming we were to try and discover if such a thing existed, how would it be possible to prove faster light energy given current human knowledge? I began to investigate, but the more I researched the possibility of FTL energy, the more I ran into the classic logical problem of proofs of existence. In fact, there's a whole history of academic science devoted to the problem of proving something exists that spans philosophy, mathematics, logic, and computer science. I'm going to give a very high-level explanation that is definitely not complete in any way, shape, or form, but hopefully will clue you in as to the nature of the zero and one problem. The proof of existence dilemma, often referred to as the zero and one problem, has been touched upon by great masters of philosophy, logic, and math. For examples, Kurt Gödel's famous incompleteness theorem essentially proves that for any given self-contained logical system of notation, it is impossible for it to prove itself completely, and it will always be possible to show contradictions in the most fundamental axioms of such a notational system. Bertrand Russell also has a famous set theory corollary, named Russell's paradox, which states that it is logically impossible for there to be a set that contains all other sets but itself. If there were such a set, it would have to contain itself, leading to an apparent contradiction. Generally, whenever scientists or mathematicians try to isolate a single self-contained system or point of reference from which to base their axioms or theorems, it leads to the 0-1 dilemma. I can rephrase the mathematical problem to be more colloquially restated as, if 0 is a singularity, and a singularity is by definition only one of something, how is 1 not equal to 0? In the context of physics and math, where we want to understand how anything can weigh more than nothing, or 0, we can restate this logical problem as a philosophical and existential problem more broadly, as, at the beginning, if there is a singularity of existence or nothing, in the absence of any external impetus, how can something else come from such a singular state? At least from a strict perspective of notational logic, this is impossible, which means that if something else other than nothing exists, which we can assume to be true regardless of notation, then there had to be something in addition to nothing at the beginning to make everything now. Wait a second, what? Now I'm babbling about things like the beginning of the universe, nothing, something, twice, everything. I was stuck here at these huge grand concepts and still had no idea how to prove anything. So I decided to put things into more concrete terms. The easiest working example in this context are the numbers, specifically the set of positive integers. Here, all the integers until infinity constitute everything, nothing is the number 0, and something is any one of the integers by themselves. While studying the accepted standard set theoretic definition of the integers designated by the ZF set theory, I found that the same dilemma exists for this notation. Specifically, 0 is defined as a singular empty set. 1 is the set that contains the empty set, 2 is the set that contains the set that contains the empty set, and so on. This means 0 is implicitly and explicitly defined using the number 1 already. 1 is defined using 2 already, 2 using 3, etc. In fact, this is a self-contained notational system in the limit, since if we spend an infinite amount of time counting plus 1, we end up at the countably infinite. Now, infinity plus 1 is still infinity, and infinity minus 1 is also still infinity. So all the integers are defined based on the number that comes after each of them, and then the system closes off at infinity. To me, this way of defining the integers is a classic example of the incompleteness theorem. On the other hand, we know that the numbers that we know work pretty darn well. So it must just be that the definition of them is incomplete. To solve this, I developed and formalized a new functional expression of definition, which normalizes a given function by the domain that it is not active over. So every function is written as a union over the domain it operates over and the domain where it is not well defined. In actuality, this is really how we think of definition, but it has never been written down this way. The full expression of this formula, accounting for all possible functions in observable spacetime, is completely intractable and so computationally infeasible. However, a clever insight is that the inverse domain of the target function approximates the full space of all their possible functions. This simplifies the expression of the function to be tractable and programmatically quite simple in fact. Once I had finished the derivation of my new formulation of definition, I was able to start to think about faster-than-light energy within this context. Since I couldn't move forward using the standard definitions that applied traveling at the speed of light would require an infinite amount of energy, my only other option was to apply my new equation to figure out how to go back in time to an older gravity. Okay, sounds crazy, but actually now I had a mechanism to search for the inverse domain of a function which could be applied to a search for gravities other than our own. Specifically, I began to think about traveling from point A to point B faster than light through gravity using not the current dominant gravity shared between them. This constrains us to older gravities since we don't have access to newer ones. An older gravity, however, is in and out of younger gravities, but not the other way around. For example, the sun's gravity is also part of Earth's formative gravity, but Earth is not part of the sun's formation. Same story with the moon and the Earth. If we think about gravity as a tree structure with the Big Bang at its head node, and Earth's moon as a terminal leaf, because gravity is a monotonic function expanding only one direction, outwards from each of our relative perspectives, then we can direct our search for older gravities up the tree starting from Earth's node. Every 2 points in the tree, no matter how distant, will eventually have shared gravity.
as we move up the tree structure, and these older gravities would conceptually allow for a shorter travel time between A and B, except for the problem of coming back to the current time. Here's a plausible trick for making this scenario work. Given points A and B to travel from to, we section off an area of the gravity tree between points A and B. Maintain a dual signature of the positions and distance between enough stars. Important to note, we do the same calculation from both point A and B, resulting in a signature pair. Since gravity is monotonic and we know the expansion rate, we can accurately calculate the trajectory of the signature going forward. If we use enough stars, then the probability of the signature happening in the past, looking up the tree, is diminishing to zero for that subsection of the gravity tree. For example, if we calculate the signature for only 2 stars between A and B, then the signature will not be unique and will have a huge redundancy in the past. If we add more and more stars to our calculation, the probability that there's a duplicate signature in this subsection of the tree with the same number of stars in these exact positions and distances from each other will be closer and closer to zero.
Here's how we can facilitate traveling faster than light through older gravities while keeping track of time.
We can search for older gravities in the gravity tree, but constraining the search within the boundaries of maintaining the dual signature of the stars between A and B. Since there are trillions of older gravities, even within the constraints of our framework limiting our search, we will still have millions of perspectives to negotiate. Due to black body radiation and the fact that every object of light emits a wave outward that expands as it moves further away from its original source, as we search through older gravities while maintaining the constraints of perspective from our computational expression of what now is, we would potentially spam point B with the wavelengths of a light-based object we are transporting from A. If we observe enough older gravities in a very fast repetitive search, then we would possibly create a wormhole that would allow for the light wave signature of an object to pass through from one side of point A to point B on the other through an older universe while maintaining the construction of the atoms now. Just a smidge of good old-fashioned motor power may be enough to push the object from point A to point B faster than thought possible with our current understanding. Voila!
Given this possible framework, I set out on applied research to understand the initial step of numerically calculating an older gravity in the tree. Without this first step, the rest of the framework is irrelevant.
To understand it simply, I encoded a simple gravity tree structure of our solar system only, with the Milky Way, our surrounding galaxy, as the root node in place of the Big Bang, with descendants the Sun, Earth, Moon, and all other planets in our solar system, and started to derive the ratio of the gravities between them. The goal was to try to understand if we could ratio out Earth's gravity, for example, and therefore access a gravity older than Earth's in front of us, and so an older universe to travel through. While working through various derivations of Newton's equation of universal gravity, I discovered a numerical anomaly that strongly suggested a wormhole signature existed that obeyed the properties I was searching for.
I began to test this with a programmable drone and started to get extremely strong flight anomalies, but they were inconsistent and very difficult to capture on camera. I continued to derive the ratio equation for dozens and dozens of other stars, moons, asteroids, and also black holes. For each and every one of them, I found the solution of a wormhole signature that depended on the independent mass between the gravitational bodies. So I decided to build a simple test using a laser beam to approximate the signature I discovered. The pulse of the laser substitutes for the flight of the drone. I've been playing with the concept of a laser-based pulse for the last 6 weeks and have already acquired the evidence that I have shown on my first video.